Equivalence relations. So an equivalence relation is nothing but a relation on a set with specific properties. We will see that the most natural way of defining an equivalence relation on a set is basically to put in relation all the elements of that set that share a particular property. And we will have an example right now. Also, for the future, keep in mind that whenever we can define an equivalence relation on a set, say A, we can split the elements of A into disjoint subset such that the union is equal to A. And then if we consider all these subsets, also called classes, basically this subset form what is called a partition of A. But this is for later. So first we have to learn what is an equivalence relation. Let me start from a kind of original example where this set is not made of numbers, letters, but is made of fruit and vegetables. So in this set, indeed, we have an avocado, a banana, some cherries, a carrot, a cucumber, and an apple. And we can represent it with this Venn diagram. And now basically we want to split the elements of this set into subsets, as I was saying. And in every subset we want to put all the elements whose name starts with the same letter. Well, you can see from the elements that we put here that we have a total of 3 possibilities, A, B, C. So basically we will have 3 different subsets, A, B, C. And in the subset A, we're going to put the fruit or vegetables whose name starts by A. So avocado and apple. In C, we're going to put cherries, carrot, cucumber. And in set B, we're going to put the banana. So it's clear here that you cannot have intersection between 2 of these sets because either the name starts by A, either starts by C. It cannot start by both. So we can represent this with a relation. So let me recall first what is a relation. We had already seen this in class, but always recalling is not bad. So recall. So for a relation we need 2 sets. So let A and B be sets. A relation R from A to B is a subset of the Cartesian product A cross B. So R is a subset of A cross B. And if we are given X in A and Y in B, we write that X is in relation with Y, so the small r for indicating that this corresponds to that relation, if and only if the element xy belongs to the subsets of the Cartesian product. Well, we can also define a relation on a set, and in this case, basically, B would be A itself. So a relation on A is a subset of A squared, and remember that by this we denote the Cartesian product of A with itself. So in this lecture we are going to focus on relations on a given set. So relations from A to A. So let's go back to our previous example where our set A, in this case I called it X, is given by this. So here, which kind of relation we were considering? Basically, taking two elements of this set, we're going to put them in relation if and only if their names start with the same letter. So we're going basically to have something like that. So for X and Y, in X, we say that X is in relation with Y if and only if the word basically X and Y start with the same letter. And so now, if we want to write down the subset of X times X that corresponds to this relation, what we have to put? Well, you will agree with me that for each X, X is in relation with itself. For instance, avocado starts with the same letter of avocado. So we're going to put avocado, avocado. And in the same way, we're going to put banana, banana, cherries, cherries, carrot, carrot, cucumber, cucumber, apple, apple. And now, well, taking as a first coordinate avocado, well, we notice that the only, in this case, fruit that starts with the same letter is the apple. So we're going to put avocado, apple. But if we could put avocado, apple, we have to put also apple, avocado, right? Because this is independent, basically, on the order. But keep in mind that since this is a subset of the Cartesian product, the order matters. And then we're going to put, of course, cherries, carrot, carrot, cherries, and etc., etc. So here already we notice something. Is that whenever we have basically AB or XY, let's say, I use XY, we will also have YX, okay? So this is true there, it's true here. And also, as I said before, we have that for all X, in R, we have the element XX, okay? So I'm looking to these cases here. And we have also third properties that we're going to notice later, okay? So this is a kind of interesting relation anyway. So what are these properties that we have to consider and study when we want to work with equivalence relations? So let me give this definition. So again, we need a set A. And let's consider also a relation R on A. Okay, so we say that R is said to be reflexive if for all X in A, XX belongs to R. Okay, let me put this in color. I don't know. And so remember that here writing this corresponds to write that X is in relation with X. And let's put this a little bit smaller. And now in another color, let's take green. We say that R is symmetric if for all X and Y in A, if XY belongs to R, then also YX belongs to R. Okay, so remember here I'm saying that if X is in relation with Y, also Y, it is in relation with X. Okay, I want to notice that this is actually an if and only if, okay? Because of course then if y, x belongs to R, because the converse is true, then we have also that x, y belongs to R. Okay, and then the last property, let's put in blue, R is said to be transitive if, this is slightly longer, for all x, y, and z in R. Again, it is given as a conditional sentence. If xy belongs to R and yz belongs to R, then xz belongs to R. Okay? So if xy are in relation and yz are in relation, also x and z are in relation. Okay, we are going now to examine these properties one by one to understand better what they mean. So let's start from the reflexive property that I have rewritten here. Okay, so remember, given a set A and a relation on A, it is reflexive, R is reflexive if for all elements of A, the pair XX belongs to R. So I want to make here a quick remark. So remember, we saw in class what is the identity relation on A, okay? This is given by the pairs XX such that X belongs to A. So, well, by definition, a relation R on A is reflexive if and only if R contains the identity relation. So if and only if IA is contained in R. Okay? Because I want that for all X, XX is contained in R. So in other ways, I'm saying that IA should be contained. So the identity relation on A should be contained in R. Okay, let's do a quick example here. Example 1. So if I take A equal A, B, C, D, and I define R to be AA, AC, BB, BD, CA, and CC, DA, and DD. Well, you will agree with me that this is symmetric because the identity relation of A, which is in this case given by 4 elements, AA, BB, CC, and DD, is a subset of R. And so, because of the remark here, we conclude that R is reflexive. Okay, let me do another example. Let's take another color. Example 2. Well, I don't like this color. Let's take this one. So in example 2, we are going to take A to be equal to the set of real numbers. And now we define our relation in this way for x and y in R. We say that x is in relation with y if and only if x is less or equal than y. Well, and again, wondering if this is a reflexive relation or not. And well, this is easy to show because I noticed that, so for all x in R, x is less or equal than x. Why? Because in particular, x is equal to x. And so this implies that x is in relation with x, which implies that R is symmetric. Okay. So we can also interpret this reflexive property from a geometrical point of view. So remember here that whenever I have a relation on a set, I can use what is called a directed. To represent this relation, I can use what is called a directed graph. In particular, when my set A is finite and with not too many elements, let's say. This is called also a digraph. Okay, for doing that, remember that I need to set up my vertices. This is the example that we did before, A, B, C, and D. And now remember that for each element in R, I'm going to put an edge in my graph, okay? So let's put some color here. AA will be the loop from A to A. Then AC will be the oriented edge from A to C. Now BB will be again a loop. Then BD will be an edge. CA will be another edge like that. CC is going to be a loop. DA is an edge from D to A. And finally, DD is again a loop. Okay? And so in particular here, we can see the fact that this is a reflexive relation from the fact that in any vertices we have a loop. If one of these was missing, then it was not an equivalence relation. A reflexive relation. Okay, so for every element, we want that, for every element x in A, we want that xx is in A, which geometrically corresponds to the fact that a loop is at every vertex. Okay, a first question for you. As always, I will give you 10 seconds for thinking. So this is the question. I have my set A given by 1, 2, 3, 4, 5, and I consider the following relation on A, which is given by the subset that contains 1, 1, 1, 3, 2, 2, 3, 2, 3, 3, and 5, 1. So I'm asking if these are reflexive relation. So 10 seconds. Well, this is of course not a reflexive relation, so the answer here is false. And the reason why is that we don't have the pair XX for every element of A. For example, the pair 4, 4 does not belong to R. So this is not reflexive. Very easy. Symmetric property. Okay, I copy again here what we said previously. So remember, given a set A and a relation on A, R is said to be symmetric if for every couple of elements x, y in A, if whenever x, y is in R, then you want also yx to be in R. Okay, so let's start from the following, let's say, exercise. For instance, if I have a set A equal ABC, I want to construct a subset of A cross A such that a subset R of A cross A such that R is corresponds to a symmetric relation. Okay, so well, I can put AA, and then in this case, whenever I put AA, of course, the symmetric of this is AA itself, so I don't have to put anything else. But imagine, for instance, that I put AC, then I have to make sure that also CA is inside, and I can put CB, but then also BC has to be inside. And then if you want, you can put BB. But in any case, this is a symmetric relation because by construction, I made sure that whenever I add a couple xy, I'm also adding the pair yx. Let's see a more interesting example. So consider the set A of integers and consider the following relation. So consider the relation R contained in Z cross Z such that for x, y in Z, I say that x, y are in relation, so the order pair belongs to R, if and only if x, y is even. So the question is this a symmetric relation? Well, the answer is yes, because here, notice that if xy is in R, which means that xy is even, but by commutativity of the product for integers, this is also y equal to yx. And so if the first one is even, also the second one is even. And so this implies, by definition, that yx are in R, they are in relation. And so, in conclusion, R is symmetric. Okay, so how in this case we can, visually, how do we see that a relation is symmetric? Well, let me take this example that we constructed in the previous slides, okay? Well, if I want to draw here the directed graph as before, okay, I have now 3 vertices, A, B, and C. And now, okay, this is not a good choice. AA becomes a loop. Then we have AC, which becomes an edge, and then CA, which becomes another edge, and then CB like this. And I don't know what to choose. No, this is I already took. Well, this is more or less the same. BC like that. And finally, oh, there is not a lot of choice here. BB is again a loop. Okay? Well, first of all, this relation is not reflexive because here at C, you see that you are missing a loop. But this is not what we are caring about here for symmetric relations. So here the fact that this is a symmetric relation can be seen from the fact that here you have this, let me do like this. Let me take a color. So it's from the fact that here you have an edge in one direction and also the corresponding edge in the other direction. And same here, you have this edge from B to C and also you have the edge from C to B. Okay, so this is how you see in the directed graph if your relation is symmetric. If you have an edge from one direction to another, you want also another edge from that has the reversed arrow. Okay, again a question for you. So consider now the relation always on the integers, which says that two integers, a and b, are in relation if and only if a divides b. So the question here is R a symmetric relation? So again, 10 seconds. Okay, so the answer here is again no. Okay. Why? Because here we want, remember that for being a symmetric relation, you want that AB belongs to R if and only if BA belongs to R. Okay? Or in other words, we are saying that A divides B if and only if B divides A. But this is definitely not true, and it's very easy to construct an example because, for instance, 3 divides 6, but 6 does not divide 3. Sorry, 3. Okay? So otherwise, if 6 was divided in 3, you would easily get a contradiction. Okay, so this is not a symmetric relation. Let's go now to the transitive property. Again, here is what we learned before. A relation is transitive if for every xyz such that xy is in R and yz is in R, then we want also that xz is in R. Okay? So let's consider here the following example. So again, let us consider A to be the set of integers, and we consider the relation R to be, so the relation on A such that for A, B in Z, we have, again as before, A is in relation to B if and only if A divides B. Okay? So again, here you're saying this corresponds to, here same thing of saying A, B belongs to R. Okay? Well, is this a transitive relation? A transitive relation, yes, because remember, assume that. Now this is a conditional sentence, so let's assume that this is true. Assume that A, B belongs, so I should say let A, B, C in Z. Assume that A, B belongs to R and B, C belongs to R. So this is equivalent to say that A divides B and B divides C. And remember here that from a result that we have seen in class that we proved already, actually in one of the homework, this implies that A belongs to C, and by definition this means that AC belongs to R, okay, which was the conclusion here. Okay, so let me just show you again geometrically what this means. So let me take the following example, very related to what we've just done. A is a subset of integers that contains only 3, 6, and 12. And then again, we're going to take the relations where AB belongs to R if and only if A, so this is in a square, such that A divides B. Okay, it's very easy here to write down R. So we have that R is equal, well, you will agree with me that every integer divides itself. So this is actually also a reflexive relation. So I have to put 3, 3, 6, 6, and 12, 12. And then, of course, I have to put 3, 6 because 3 divides 6. I have to put 6, 12. And I have to put 3, 12. Okay, now here we will notice that 3, 6 is here, 6, 12 is here, and this plus this implies that 3, 12 is also here, okay? If x, y, and y, z are in R, then also x, z is in R, okay? So if we draw here the directed graph, which has vertices 3, 6, and 12. So, of course, we have now, let me just do like this without specific color, some loops at every vertices, and then, let me remove this, 3, 6 tells me that I have this edge. Over here, 6, 12 tells me that I have this edge over here. And now, whenever I have an edge from 3 to 6 and from 6 to 12, I will have also an edge from 3 to 12 directly, okay? Which corresponds to the fact that 3, 12 is in my relation. Okay, a question again for you, which is the following one. So consider the set A equal 1, 2, 3, 4, 5, and consider this relation R on A, which is given by 1, 1, 1, 5, 2, 2, 2, 3, 3, 3, 4, 2. Now, this is not a transitive relation, but I'm telling you that by adding only one of the following elements, you can make it transitive. So the question is, which one? 5, 1, 3, 3, 4, 3, or 3, 2. 10 seconds. Okay, so let's think to this. basically, here what is the problem? Here, for instance, the problem is that I have 4, 2, okay? So let me call this x and 4x and y and 2y. Then I have 2, 3. So in some sense, this is the same y, and then 3 is a new z. But is x z in R? Well, xz is for 3, which is not in R, and so it is what I have to put. And then you can check actually, okay, 3, 3, this was very stupid for putting it there, it is already there. But sorry, so this was stupid, but you can check that adding 5, 1 will not make it transitive, and neither 3, 2. And that is, with that element, actually, your relation becomes transitive, okay? Now, very easy, the last part. What is now an equivalence relation? Well, this is a definition. A relation R on a set A is an equivalence relation if all the following hold. R is reflexive. R is symmetric. And R is transitive. So R is all the properties that we've seen so far. So the easiest example, like the trivial example, is given by the identity relation. So for every set A, the identity relation IA equal XX, such that X belongs to A, is an equivalence relation. Okay? So this is very trivial. If an element, basically an element is, you're saying that an element is in a relation. So here what you're saying, that given X and Y in A, you're saying that X, Y is, so X and Y are in relation if and only if X is equal to Y. And it is trivial to prove the properties that are stated above. A more interesting example. So imagine you have A, which is equal to Z, so the set of integer, and take X, Y in Z. And you say that X is in relation with Y if and only if X and Y have the same remainder when divided by 7. So example, if I take X equal 17 and Y equal 31, Then you have that x is in relation with y. Why? Because, well, 17 is equal to 2 times 7 plus 3, while 31 is equal to 4 times 7, again plus 3. And remember that this is the remainder. Okay? And actually, what you can say here, this is an equivalence relation because, of course, an element has the same remainder of itself when divided by 7. This property clearly does not depend on the order of x and y. And in the same way, you can prove the transitivity. If x and y are the same remainder and y and z have the same remainder, of course, x and z will have the same remainder. Okay, so I have a last question for you before leaving you, and it is the following one. So I'm going to list several sets here, and among these, only one consists of integers that have all the same remainder when divided by 5. So which one? 27/2020, 6/31/1991, 4/8/12. 10 seconds. Well, let's say in the first one, well, it is true that 2 and 7, they have the same remainder because 2 is 0 times 5 plus 2 and 7 is 5 times 1 plus 2. So here the remainder is equal to 2. But for 2020, well, 5 divides 2012. So this means that the remainder here is 0. So these three do not have the same remainder. In the last case, well, 4 as a remainder 4, 8 as a remainder 3, because 8 is equal 5 times 1 plus 3, and 12 as a remainder 2. So for sure, these do not have the same, while here they all share the same remainder, and this is equal to 1. So this is the correct answer.